Welcome to a lesson with Dr. Powell. Let's talk about the monotone convergence theorem and what that is. So monotone means like one tone. Well, one quality maybe of either going up or going down, but not doing both. So monotone, a function is called a monotone function if it's increasing or if it's decreasing, and it's never constant. Well, constant. So we don't want that. So it's either increasing or decreasing, but it's not doing both either. Not that as well. So for a sequence, that means the sequence. So if we draw a graph of the sequence, it looks like this. It's only ever increasing. So from term to term, one term is higher than the last one in its output value, or it's always decreasing. So this guy's always less than the previous guy. Something like this, always less than what came before. So that's what monotone means. So the monotone convergence theorem is a theorem about the convergence of a monotone sequence. Okay, so let's take a look at that. What does it say? Well, let's suppose we have a monotone sequence, and let's just suppose that this one is increasing. And also suppose that we also know the sequence goes on forever, and we know that there's a line that it never crosses, but you also know it's monotone. Then what you have actually shown is so if you have a function that's monotone, and you know that this function is bounded above, so it's monotone increasing, and it's bounded above, then we actually know that this sequence will have a limit. That's all this theorem states. If the values of the function, so let's take a look at this. So if the values of the function, so if we think about the number line here, we could picture it this way. And suppose that you have a sequence element here, and then another one here, and the next one here, here. So they're all going in this direction. And suppose that they're bounded. So there's a line that bounds that these will never go past, even though they're always going this way. Monotone convergence theorem states that such a sequence will have a limit somewhere, that it won't go past, and that it will actually limit toward. Now, it is a fundamental axiom of the real numbers that any set, so in particular, you can take the set or the collection of all points on the line that represent sequence elements, say. So suppose you can picture your sequence as points on the number line. And suppose that's a set, call it the set S. So there's an axiom of the real numbers that says given any set S that is bounded above, so there's some point that it doesn't go past, that there's an axiom that says there's actually a least upper bound. I mean, there's lots of upper bounds. This is an upper bound here, but I could have also drawn the line here. This is also another upper bound, or this one. But there's a fundamental axiom. That means something, a fundamental assumption, just something we assume about the real numbers, is that there's a least upper bound. So all these upper bounds, there's a least one. Now that least one ends up being the limit itself for a monotone sequence. So monotone, it keeps on getting higher and higher, but the smallest bound that bounds everything actually ends up being the limit itself. Now, the bound is actually, technically speaking, is a point that's greater than or equal to any element in the set S. So potentially the limit could be hit, especially if you have stabilization. Like what if you have a sequence of things that went like this: 1/2, 3/4, then 1, then 1, and then 1 forever. This has an upper bound of 1. And because 1 is greater than or equal to everything in here, it stabilizes there, and the limit is achieved within the set itself. And it is also the least upper bound. So the monotone convergence theorem just kind of makes that precise to just say, hey, if we are increasing and we're bounded and we at least have one bound above, then we definitely will have a limit. So all we have to show is that we have a bound and that it's increasing, and then for sure we have a limit for our sequence. This theorem does not say what that limit is. It just simply says there is a limit. Now, we could also look at it backwards the other way, just kind of in reverse. So let's just kind of rewind here and look at things in reverse. So suppose we have a sequence. Okay, on the number line, it starts here, but what if it goes down the other way? So it's monotone because it's always decreasing. That also means monotone, means that it would be monotone by the definition of monotone. So it's decreasing. And if it's bounded below by something, the same reasoning and reflection will tell, the theorem will tell us as well that this also has a limit. So there'll be some limit for this particular sequence going down that way. So that is the statement of the monotone convergence theorem. Thanks for watching.